7 base units of the SI system. So the SI system replaces all traditional units of measurement, except those used for time, with 7 base units for 7 physical quantities assumed to be mutually independent. So when you talk about something that has a length, the base unit is the meter. Everything's based on the meter, which is approximately a yard. Meter's a little bit longer than a yard, for those of you who really don't know what a meter is. A mass, the mass unit, which is how much stuff something has, right? How massive it is. The base unit is the kilogram. Now the kilogram is, if you buy a kilogram of sugar, that's about 2.2 pounds of sugar if you're using the US system to compare. Temperature is the Kelvin scale. And as I said before, Kelvin is basically the same thing as Celsius, but you just add 273 degrees. The amount of a substance, that's how many parts you have, is called a mole. Okay? A mole is a really big number, because when you talk about how many atoms something has, you say, okay, there's 12 grams of stuff for 1 mole of carbon. I'm not sure if it's 12 grams or 28 grams. It might be 28 grams. But anyway, a mole is a huge number. There's 6.023 times 10 to the 23rd. So that's 6 with about 23 zeros after it. And that's the number that's in a mole. The number of grains of sand, the number of atoms in a mole, the number of stars in a galaxy. Those kind of things could be expressed as units of measure relating to the mole. Of course, we have electric units. There's a unit called a current. The unit's called the ampere, and it represents the physical quantity of current. So current is basically how many electrons you have coming by within a second coming down a wire, for example. So that's called an ampere. And most of the electrical currents we're used to seeing are in milliamperes, microamperes. You don't need a lot of current to run a cell phone, for example. So those will be in very small parts of an ampere. Now if you're running a city, then you're talking about mega amperes that you might have to deliver to a city. Okay, luminous intensity. So how bright something is, how much light is falling on a surface, it's called a candela, and that's labeled as a CD. That's its unit. And of course we have time, which is in seconds. So time is, let's see, there's 60 seconds in a minute, 60 minutes in an hour. If you don't already know that, you should write that down. And then there's 24 hours in a day and 365.25 days in a year, etc., etc., etc. We deal with milliseconds, microseconds, nanoseconds, very small portions of a second when we're talking about microsystems and electrical signals and how fast switches turn on and off. We're usually much, much faster than a second. And derived quantities are quantities you get when you look at the base unit. So if you're talking about area, that's derived from the base unit of length. So a length times a width is an area. And volume, of course, is length times width times height. Then you have speed and velocity, or rate, how fast something moves. That's based on the meter and the second. So you'll have meters per second. Then you have acceleration. How much faster do you go in a second? So if you go from 2 meters a second to 5 meters a second over a period of 1 second, you're going to go 3 meters per second squared faster in that time. So that's velocity per second, how much change in speed or change in velocity you have in a second. Wave number is a reciprocal meter. Wave number is used in spectroscopy. We won't use it much in microsystems courses unless we're talking about optical sensors and what their response is to wavelength, to light. Mass density is the next one. That's your basic density. How many kilograms do you have in a cubic meter? So how much stuff you have in a unit volume. So water has a different density than air. Correct? Right? That's why a balloon floats on top of the water, because the balloon is lighter than the same amount of volume of water. So you get a buoyancy effect. Specific volume is basically how many cubic meters there are per kilogram. So instead of kilogram per cubic meter, you have cubic meter per kilogram, and it's just the reciprocal of the mass density. Current density, for example, are amperes per square meter. So that's interesting if you're trying to figure out how much electricity is going through a wire, through the cross-sectional area of the wire. As the wire gets bigger, gets thicker, you have more area, so you can push more current through it. It's kind of like a pipe and water flowing through it. You can push more water through a bigger pipe. Magnetic field strength, that's ampere per meter. Okay, now that's kind of a strange unit, and when you work with magnetic systems and magnetic sensors, it becomes important to characterize your sensor as to what it can actually detect. So maybe your sensor puts out a voltage that's proportional to the amount of magnetic field it senses. So you would have to do a calculation to look at the magnetic field strength and compare it to the voltage output of your sensor. That way your customer who's buying your magnetic sensor would be able to tell how sensitive your system is and if it will work for his application. Amount of substance concentration is mole per cubic meter, so that's how much stuff you have in a cubic meter. Now many times these types of things are such huge numbers that they may say how many moles per cubic centimeter or how many moles per cubic millimeter. Luminescence or luminance is candelia per square meter. So that's an interesting unit. You might want to be looking at how much light is falling on a square meter of surface, so that when you make your solar panel, right, which converts sunlight into electricity, you can get an idea of how much electricity you will get out of that solar panel. That's why that kind of unit can be very useful for the technologist. So candelia per square meter is another one of the derived quantities. So we have our base units, and then from those base units we can put them together and come up with a derived unit. So depending on what types of applications you're working with, you'll probably be using derived units more than actual base units. So here's a challenge for you. Write an algebraic equation for each of the following. Your answer should result in one of the derived units of the SI. So if you have a volume of a cube, right, that's 3 meters by 2 meters by 6 meters, how do you find out what the volume is if the cube is that size? Well, you would just want to multiply them out. So you go 3.5 times 2 times 6.3 meters. Each one of meters would be something that's about 7 times 6, 42, a little over 42 cubic meters. And remember, I said cubic meters because you're multiplying the units too. So if you're trying to determine a volume from the shape of an object and you do the math, you should come up with meters cubed, m to the 3rd power. If you don't, you did something wrong. Okay? The speed of a car that traveled 88 kilometers in 45 minutes, how would you calculate that? Well, you could say so many kilometers per hour. So you'd have to convert your minutes to hours. If you did that, you went, what, about 3/4 of an hour. You went 88 miles. So just off the top of my head, that's something like 88 times 4 would be 320 something divided by 3, about 100 kilometers an hour. That's how fast you go. Now use a calculator and just go 88 divided by 0.75, because 45 minutes is 3/4 of an hour, and 3/4 is 0.75, so you can use a calculator to do it. Or if you do it by hand, you have the 3/4 in the denominator of 88 divided by 3/4. You can solve it algebraically by hand, and I suggest you practice these sorts of things. Now, how do you convert it from kilometers per hour to meters per second? That's another challenge. Okay, so here's what we see the answers to be. So you have 88 kilometers times 1,000 meters per kilometer. So you're converting the distance to meters. Okay, so you look at that and you say, okay, why does that work? Well, the kilometers will cancel out. Okay, and really what you're doing is multiplying by 1. Because you have 1,000 meters in 1 kilometer. That's 1, right? If you look at that and say, that's like multiplying the number by 1. And that's a good trick to keep in mind. You can multiply anything by 1 and still have the same quantity of stuff. So 1,000 meters divided by 1 kilometer is really 1. It's 1 unit. All you're doing is changing it from one type of unit to another. So you have 88 kilometers times 1,000 meters per kilometer. So the kilometers cancel, and now you've converted kilometers into meters. Then you have to convert minutes into seconds. So here we've multiplied 45 minutes times 60 seconds per minute. Well, 60 seconds per minute is like multiplying by 1. So we haven't changed mathematically anything. We're changing just the units. Okay, so the minutes cancel out and you're left with seconds. Okay, and now you have seconds in the denominator. Now you have to look at this carefully because the division sign, we're writing this out in a line, so it's kind of hard to see. I would suggest writing this down and convincing yourself that this is true. Okay, so we have to define the 7 base units. As with most units of measurement, the official definitions for the 7 base units of SI, System International, have changed throughout the years. We can never keep anything the same. We always have to change things. The most current definitions are those established by the International Bureau of Weights and Measures. These definitions are another aspect of SI and are updated every 4 years at the conference. So the meter. The first definition of the meter was defined by the French Academy of Science as 1/10,000,000th of the distance from the equator to the North Pole. Well, that distance, depending how you measure it, may change every once in a while. The meridian that was used was the one that goes through Paris. In 1983, the General Conference on Weights and Measurements replaced the definition with the following. The meter is the length of the path traveled by light in vacuum during a time interval of 1/299,792,458 of a second. Okay. Well, now we're basing distance on how far light travels in a very short amount of time. That's okay. That's invariable. If you take the distance from the North Pole to the equator, the Earth might change its shape over time. Okay. It might get a little bit flatter. And that distance along that line could change slightly. But the distance that light travels in that amount of time that's quoted there doesn't change. That's assumed to be rock solid. The speed of light doesn't change. It's constant. Doesn't matter what happens to the shape of the Earth or anything like that, as far as we know. The kilogram was originally defined as 1,000 times the absolute weight of a volume of pure water equal to the cube of the 100th part of a meter. So you take a cubic meter, right? You take 1/100th of it and then fill that volume with water, and the mass of that water is equal to a kilogram. And we still use that today. 1,000 cc's is a kilogram of water. I use that all the time when I'm converting from cubic centimeters to milliliters, for example. Okay, and of course the temperature matters, because at higher temperatures water expands a little bit, its density is slightly different, so the mass won't equal quite as well. So the definition was good for a while, but it was decided later to change the definition to the mass of a cubic decimeter of water at standard pressure and temperature. Then in 1889, the CGPM sanctioned the international prototype of a kilogram and declared that this prototype shall henceforth be considered to be a unit of mass. So, in my opinion, they went a step backwards, because pure water is H2O. It's chemically defined, and it doesn't change, over time. Water is water. And they could have based the unit on so many molecules of water, but they decided to create a standard kilogram mass and say, okay, this one piece of metal is a kilogram of mass. And that's okay to do, but what happens if that one piece gets moved, if it gets damaged, if it's in a fire? It can change for whatever reason. And actually, in the newspapers recently, and I'm talking in 2007, there was a bit of a controversy that the standard mass and the backup mass changed relative to each other. Their masses changed, and they didn't know why. So now we have a problem again. So I'm sure in the future the kilogram will be based on something else.